Okay, so let's take a look at our lesson on polar coordinates. So before now, we've basically been working with a different type of coordinate system. And this coordinate system, we have a couple of different names for it. It can be called a rectangular coordinate system or Cartesian coordinate system. And we are accustomed to, this is what we've been working with for years, right? We've got the X and we've got the Y. We know there's 4 different quadrants. We kind of know how that works. You know, if I'm going to plot a point, you know, let's say I plot the point 3, 2, I know exactly where to put that point 3, 2. Okay, it's just something we are quite familiar with. What we're going to be learning today, we're going to be learning the basics of a different coordinate system. This different coordinate system is called the polar coordinate system. And it has some definite benefits that you will see in different contexts later. So there are some reasons why we might want to plot in polar rather than rectangular. But what we're going to learn now is just how do we do that? How do we plot points in polar? How do we work with the polar coordinates? So instead of our points being in X and Y like we're accustomed to, in polar coordinates, our points are in R and theta. R represents, it's kind of like a radius, if you will. You think about the unit circle. We're going to be using the unit circle, which is why we put this right together right after we had a lot of work with the unit circle, because it still should be fresh in your mind. So this distance right here, the distance from the origin, which they call the pole. Now you don't have to, you can call it the origin if you want to, that's fine. The pole or the origin. So the distance from the pole to the point that we're plotting is R. So R is a distance kind of like a radius. Or with the grid that we're going to be using, kind of like rings. On the grid, it's the rings. And then theta is theta is the angle that's measured from the polar axis. The polar axis is basically the X, or what we would think of as the X-axis. They call this the polar axis. And so the angle measure, if we're on a positive rotation, we would be going counterclockwise like we are accustomed to. And if we had a negative rotation, we would be going clockwise. So we have the same characteristics of angles that we have in the past. That's exactly the same. Okay, so that's how we're going, and we're going to practice plotting points. So R is the distance from the origin or pole to the point, and theta is the angle measure between the polar axis and that segment that we could draw between the origin or pole and the point. So that's an overview so far of the graphing. Are there any questions on the overview? Okay. So the next thing is we're going to be able to go back and forth between the 2 different coordinate systems. So we're going to be able, if we're in rectangular coordinates, we would be able to put it in polar coordinates and vice versa. We're going to be able to go back and forth. And I want to really emphasize that the point, so let's say we wanted to plot, let's say this point was what? It was 3, 2. If we have our polar grid, you know, with all of our angles, that point is going to be in the exact same spot. The points aren't going to move. If I will overlay the polar coordinate grid on top of the rectangular grid, the points will match perfectly, as will the equations. They will look exactly the same. So we're not changing the way things look. So this would be our theta, and this would be our R. We're not changing the way they look, we're just changing how we plot them and what information that we need. It's going to be the same spot. Really important for us to understand, because as we go back and forth between the 2 coordinate systems, if we don't really have the idea that the point is in a particular spot and we need the new point to be in that same spot, we're going to have some issues. Okay, so please note that they will match up perfectly. When we convert, if we're simply converting points, if we're going from, let's say, if we want to change from a polar coordinate system to a rectangular coordinate system with points, okay, this is with points, we would use these two formulas, x equals r cosine, y equals r sine. That's what we would use. And it probably doesn't surprise you that x is matched up with the cosine and y is matched up with the sine, because that's our norm, right? That's what we've been doing. X is mapped to the cosine and y is mapped to the sine. So that's probably not a surprise. If we're going the other way, if we're going from rectangular, and this is for points, to polar, then we would use these two equations. R squared equals x squared plus y squared, and tangent theta equals y over x, which kind of makes sense because tangent is sine over cosine, sine maps to the y, so it kind of makes sense how everything is structured. Okay. All right, so everybody okay so far? All right, so let's look at some examples. The first thing that we're going to do is we're going to plot points. We're just going to plot some points. So let's focus on the first point. So the first point, this is my r and this is my theta. So when we are graphing on grids like this, you can think about, I call them the rings. You can think about these rings as, ring 1, ring 2. So this will be R is 1 and R is 2, so forth. Just you count the rings out. That's a unit of measurement that we're using for R is the rings. So what would I do? I would go to 3 pi over 4. And so we would rotate all the way around to 3 pi over 4. And then I would go out 1 ring. So that would put me right here. And this would be point A. So I'm rotating, because this is a positive angle measure, I rotate from the the polar axis, all the way to 3 pi over 4. Okay, that's a pretty straightforward example. Now let's, part B is a little bit different in that we have a negative angle measure. And the negative angle measure means the same for us as it did in the past. If I've got to go negative pi over 6, I'm going to start here and I'm going to rotate backwards, right? I rotate backwards to get to the negative angle measures. So negative pi over 6 would fall here at 11 pi over 6, and we would go out 3 rings, and this would be the location of point B. Okay, so everybody okay? All right, on the point at C, again, something a little different going on. We've got the angle measure of 3 pi. We know that's more than 1 rotation. And so if we think about it, we know that this would be pi, that would be 2 pi, and this would be 3 pi, right? 3 pi would be back over here. This is where 3 pi would be at pi. So I would go to that angle measure. So we are focusing on this angle measure, and we go out 5 rings. So 1, 2, 3, 4, 5, and this would be the location of point C. So far we have done several things with our angles. We have our first one, this is just a regular angle, 3 pi over 4. The second one, we practiced a negative rotation. And the third angle, we practiced more than 1 rotation. So we've looked at pretty much the vast majority of the possibilities for changing the angle. All right, now we're going to look at something very strange, and that is changing the sign of R. So let me refer you back to our Cartesian coordinate system. We know where positives and negatives are in the Cartesian coordinate system. We know that x's are going to be negative over here, right? We know that. That's where x is negative. We know that y's are going to be negative down here. We know that. Okay, it's a location. That is not the case with the polar coordinate system. We don't have a section that's designated negative like we do in the rectangular coordinate system. That is not a thing. It is not a thing. So how in the world do we get a negative r? So let me explain. So what we want to do is we're going to look at pi over 4. So pi over 4 is our focus. So I'm just going to draw, this is where we want our point, that's the angle measure for pi over 4. Okay, so we're at pi over 4. If we had pi over 4 and a positive 4, that would simply be 1, 2, 3, right here, right? A positive 4 would put me right there. It would put me in the same angle measure that I'm supposed to be in. Here's what happens on a negative r measure. If r is negative, what it does is it takes you and it shoots you directly straight across to a completely different coordinate. So instead, what it's going to do is it's going to shoot us across over here, and it's going to put us on the 5 pi over 4 line. That's what a negative r will do. It basically, if you could think about it, it's like you changed by 180 degrees or by pi. You've changed locations by an entire, and again, you can think about it in degrees or radians, 180 degrees or pi. So our point, negative 4 pi over 4, is actually going to be over here, 1, 2, 3, 4. It's going to be right here. That's where our point D is going to be. Is going to be straight across from where it would have been. That's how we do negatives with r's. Does that make sense? It just kind of, that's the only kind of really weird thing that we're not accustomed to. We've been dealing with all those different angle situations before. We know how to do a negative angle measure and how to do more than one rotation. We know all that. This is actually the only thing that's brand new for us. If we have a negative r, it forces us to go, if we're in, we would kind of, if we want to think in Cartesian coordinate system thinking, we could think about this as being quadrant 1, and this is being quadrant 3. So if I am an r, and my angle's in quadrant 1, and my r is negative, it's going to shoot me across to quadrant 3. You can think about it that way as well. All right, how are we with the graphing? Is everybody okay? Okay, so now let's work on converting back and forth. Or actually, the first thing we're going to work on is something that we've done this before. Does anyone remember what coterminal angles is? Remember that word from long ago, way back in the depths of our memory? Coterminal angles. Does anybody remember that? Yes. Coterminal angle, like pi over 4. What would I do to get a coterminal angle for pi over 4? I would add 2 pi or subtract 2 pi. Remember that business? Yeah. Okay, good. That's what we're working on here. We're going to be using that concept of coterminal angles. We're going to find 2 other polar coordinate representations of this point. 2 of them are going to have r being positive, and 2 of them are going to have r being negative. So that's what we're working on. So let's work on the r being positive. Okay, that's probably the easiest. So 2 is going to stay at 2, and 2 is going to stay at 2. So we just need a coterminal angle with the pi over 3 to find 2 other representations for that location. So I add 2 pi to pi over 3, so that'd be what, 6 pi over 3 plus pi over 3 would give me, what, 7 pi over 3? Okay, that's 1. And just for fun, why don't we just subtract 2 pi as well? So I have, let's see, pi over 3 minus 6 pi over 3 would give me, what, minus 5 pi over 3. So our positive r's are pretty straightforward. We're just doing our coterminal angles. The negative r's are a little weird because negative r is weird, I'm just going to say. I don't mean to hurt its feelings, but it's just kind of weird. Okay, so we've got -2 and -2. We're going to have to come up with the angle measure. So let's kind of focus over here on our coordinate grid over here. So I need to be at pi/3. So this is kind of where, this is my angle measure, pi/3, 2. This is where I want my point to be, at pi/3, 2. Okay, and I have two representations with the +2. That's working good for me. Now I need a representation with the -2. So if my r is negative, then my angle measure has to be directly opposite of where I am. Are you with me? Directly opposite. So my angle, to get my point to be where that purple line is, my angle needs to be over here. Right? My angle needs to be over here. So this is, you know, where I am with a positive r. With a negative r, I need to be over on the pink side. That needs to be, because if I am on the pink angle and I have a negative r, it's going to shoot me across to where the yellow is. Does that make sense? Okay, so here we go. Let's see. So, well, that's nice. I could use just 4pi/3. That's a good one. And now I'm doing coterminal angles. I just need an angle that's coterminal with 4pi/3. So I'm simply going to add 2pi or subtract 2pi from that. I actually subtracted 2pi from that, and I got -2pi/3. Okay. We good? All right, so let's look at number 3 and 4. We are converting points from one location, one coordinate system to another. In number 3, we're going to go from polar to rectangular. And on number 4, we're going to go from rectangular to polar. We're just going to practice both of those. And in doing those, we're going to use these formulas up here. These are the formulas that we're going to use. If we're going from polar to rectangular, we're going to use the ones in the blue. And if we're going from rectangular to polar, we're going to use the ones in the green. That's what we're going to do with points. Okay. Now all bets are off when we're doing equations, but with points, that's the way you do it. All right, so this is my r, and this is my theta. And by the way, just like this is my x and this is my y, they have to be in that order. They have to be written in that order. That's not like you can switch them around. That's not okay. So we've got x equals r, which is 4, cosine theta, which is 2pi/3. So now it's just a matter of our unit circle values. So let's think about 2pi/3 is 4pi/6, which is right here. So cosine is negative in the second quadrant, and that's taller, so that would be what, -1/2. And so x is going to be a -2. Okay, so now let's use our y formula. So y is r, which is 4, sine of 2pi/3. So y is going to be 4 times, so it's the same location up here. Y is positive in the second quadrant, and it's longer along the y-axis, so we're going to use the bigger number, which is √3/2. So y is going to be, what, 2√3. So our point is -2, 2√3. It is actually very wise for us to double check. I'm just telling you that that would be wise for you to double check as you get into your homework in the textbook. Some ladies are just really forgetting that the points have to overlay each other. So if this point right here at 4, 2pi/3, if we go look over here at 4, 2pi/3, we should be, you know, over here in the second quadrant. This needs to be in the second quadrant. If that point is not in the second quadrant, then we have the wrong point. And I know I've said that in several different ways. I just need to be sure we check that. If that point is in the second quadrant, the other point has to be in the second quadrant. They have to match. So these both are in quadrant 2. Okay, so that is going to apply to this as well. So if I've got an x of 2 and a y of, so x is 2 and y is negative 2, I'm going to be in quadrant 4. Whatever polar coordinate I come up with, better put me in quadrant 4 or I'm in the wrong spot, because they match perfectly. So now let's use the other two formulas. So we had r squared equals x squared plus y squared, so 2 squared plus negative 2 squared. So r squared is, let's see what that's, 8. So r is going to be plus or minus, and the square root of 8 reduces to 2 root 2. Now it just depends on how we want to write the point. I actually prefer using positive r's. I don't know, if you want to live on the edge and you want to use a negative r, go for it. They're harder, but you can. You just need to be sure you're in the 4th quadrant no matter what you do. Okay, so there's my r. I can use either one. Let's find our theta. So tangent theta equals y, which is negative 2, over x, which is 2. So I need to think about where tangent is negative 1. Now there's a couple of places where tangent is negative 1, right? Which place do I want? I want it to be in the 4th quadrant. That's what I want. Because why? Because the point that we're trying to rewrite is in the 4th quadrant. So we could go a backwards rotation if we wanted to. Theta could be negative pi over 4. That's okay. Or we could do a frontwards rotation. That's fine too. So if I go around the positive one, it would be 7 pi over 4. And since I want to just be in the 4th quadrant, I don't want to be crazy, right? I'm just going to use the positive r, so 2 root 2, and I don't know, let's do negative pi over 4. Now, if I wanted to use a negative r, this is just a what if I wanted to use a negative r, which quadrant should my angle measure be in? Which one? Very, very close. Very, very close. Second. Why? Because it would shoot you straight across, right? Like 180 degrees across. So if I wanted to use a negative r, I would have to have my angle in quadrant 2. Okay, are we all right with that? Yes? Okay, thank you ladies for being brave and answering me. Now, okay, so I'm hoping that these things right here, they're pretty straightforward. They are pretty straightforward after we get used to them. The way that you graph the points is not going to change. The way that you find different locations for the points or different representations for the point is not going to change. The way that you go from rectangular to polar and back and forth with points is not going to change. Okay, the only weird thing is changing equations to the different forms. That is weird. I'm just going to tell you. That's probably the hardest part of what we're going to be doing today, is switching. Now, number 5 of the two kinds we're going to switch, number 5 is the easier one because it's easier to go from rectangular to polar. Because what am I going to do? I'm going to use x equals r cosine theta, and I'm going to use y equals r sine theta, and I'm just going to sub those in for x and y. That's it. Then I have to work on it to get it in the right form. I'd like for you to look at the way the polar equations are. See how they look? It's like an r equals with a bunch of thetas, right? That's what it looks like. That's what I'm going to have to make my answer in 5 look like. It needs to be like an r equals with stuff. So here we go. I'm going to replace the x with r cosine. So I've got r cosine theta, and that x is squared equals 4 times r sine theta. That's what I have. So here's my goal. You all know I like to write steps. I'm going to write the steps out. In this kind of problem, my goal is number 1, no fractions. And number 2, a small number of trig functions. So the smaller the better. Small number of trig functions. Okay, that's my goal. All right, so let's clean this up. So I've got r squared cosine squared equals 4r sine theta. Okay, so our techniques, I'm going to start listing techniques. These are the most common techniques that we use for going back and forth with equations. So a first technique we can use is we can divide by r. It's okay to divide everything by r, because I got too many r's there. See, I've got an r squared and an r. That's too many. So it's okay to divide by r. So that's what I'm going to do. I'm going to divide both sides by r, and that's going to give me r cosine squared equals 4 sine. So let me move this over just a bit. Okay. Now we need to solve for r. See how these equations are? They need to be an r equal thing. Okay, so I'm going to solve for r. I've got r equals 4 sine over cosine squared. Okay, great. That's great. We have it, r equals something. So in looking at what we're doing, our goal is number 1, no fractions. That's our number 1 goal, no fractions. Okay, well, we know a lot of trig stuff by now, right? You're like, yes, yay, we get to use the identities again. Woohoo! Aren't you sad and so happy that now you're happy that we get to use them again? You probably thought, oh no, I'm never going to get to use the quotient rule, quotient identity again. Okay, maybe not. All right, so I have 2 ways that I can fix that. I can do, what is the reciprocal for cosine? What is the reciprocal property for cosine? Cosine is what? Is secant, right? They're reciprocals. So I could change this to 4 sine secant squared. I could totally do that. And I've accomplished both of my goals, which is no fractions, and I only have 2 trig functions. Or, and we'll have to see what your textbook wants you to do. It probably is going to give you some guidance on how to simplify. What if I did sine over cosine? We know what sine over cosine is, right? What's sine over cosine? Tangent. So what if I did 4 tangent, and then there's 1 cosine left on the bottom? I brought it up to be secant. So that's another possibility. We know with trig, we got lots of things going on. But those are 2 perfectly acceptable ways of rewriting our equation. Okay, so what that means is, if I put this in my grapher, if I graphed this, so let's just circle them, okay? The graph of this and the graph of these are going to be identical. You can overlay them. They're going to be the exact same, okay? But of course you would need to be in radian mode to graph with the thetas. Okay, so now let's go the other way. Okay, so I need to be more specific about what this means because every year students are maybe confused. So I want to be very specific what this means. This means, number one, if we're going to go from polar to rectangular, it means, number one, no R's are left. Once I convert, there can be no R's, period. And number two, no, this is the one that students typically, I don't know what happens, but they kind of leave trig in there. There's no trig. No trig functions are left, which means there's no thetas. There are no thetas left, period. That's what this means. To go from polar to rectangular, I can't have any R's left and I can't have any thetas left. Otherwise, I haven't converted. I can only have X's and Y's. That's it. Okay, so here we go. We got some more techniques. These are the techniques that typically work for this version. So number one, this is what 95% of the time you're going to use one of these things, one or more. So what do we try to do? We want to try to get all sine and cosine. So we can convert those. That will make our life easier, right? We want to get all sines and cosines. If we don't have sines and cosines, we want to try to turn it in there. Number two, we can multiply both sides by R. That's a thing that we normally have to do. Multiply both sides by R. And lastly, we can square both sides. These are the most common techniques that we will use on problems like this. And I think it's really important to have them written out. Otherwise, you won't have a place to start. So let's look at part A. It has secant in it. I don't want secant in it. I want cosine. So the first thing I'm going to do is I'm going to try to get it into be cosine or sine. We know secant is the reciprocal of cosine. So let's rewrite this as 5 over cosine. Okay, good. We did our technique number one. That's great. Now I need to use, so let's look at the formulas we're using. You know, we're using these, those guys. We're also using the R squared guys. These over here, these are our formulas that we're using. R squared equals x squared plus y squared, tangent theta equals negative y over x, and x equals r cosine, y equals r sine. Those are the formulas we're using. And I am so close on part A to get r cosine. I'm so close. Why don't you can think of it two different ways. You can think of it as cross multiplying. That's okay to think of it that way. Or you can think of multiplying both sides by cosine. Either way, I get r cosine equals 5. So we know what r cosine is, right? It's x. So x equals 5. So the graph of x equals 5, we know in Cartesian land, looks like this. That's the graph of x equals 5. And if you graph 5 secant in polar, you're going to get the same graph. You're going to get a vertical line that looks just like that. They will overlay each other perfectly. Okay, so really important for us to recognize that we are creating the same graph in the two different coordinate planes. Okay, are we okay? All right, part B. Ooh, let's see, I don't have near enough R's. I wish there was an R with the 2 cosine. So I'm going to do technique number 2, and I'm going to multiply both sides by R. That would make me happy. So let's multiply everything by r. So that gives me r squared equals 2r plus 2r cosine theta. I multiplied everything by r. And as soon as I can convert something into x's and y's, I do it. We know what r squared is, right? R squared is what? X squared plus y squared. So I'm going to replace r squared with x squared plus y squared. Okay, I'm going to leave the 2r there. I don't know what to do with it yet, but we'll figure it out. I know what r cosine is, right? What's r cosine? R cosine is x, right? So that's 2x. All right, yay. Oh my goodness, we are getting close. Well, we still have an r left. That's not okay. So what I'm going to do is I'm going to isolate the r. I'm going to get it by itself. Okay, that's what I would suggest that you do on a problem like this. Get what you have left over, get it by itself. So, okay, so I'm going to rewrite and I'm going to switch sides. I hope that doesn't disturb you. I'm going to put the 2r over here just so it's easier to work with. X squared plus y squared minus 2x. Okay. All right, let's look at our techniques. We already did the multiplying both sides by r right now would make it worse. We don't want to do that. What if we squared both sides? What about that? Wouldn't that give us an r squared? Won't that make us happy? Yes, that would make us happy, right? Because r squared is x squared plus y squared. Yay! Y'all are looking at me like, oh my gosh, she's crazy. It's okay. We want to get rid of it, right? We do. So let's square both sides. So squaring both sides, we've got 4r squared equals, please, please do not, I know you're tempted, do not FOIL all that out. Don't do that. Leave it alone. Just leave it alone. And I'm going to switch the r squared to be x squared plus y squared. And we're just going to leave it alone. When it's this complex, we do not want to continue messing with it. Now, perhaps we can see, let me point this out. I want us to understand. If I graph this in Cartesian coordinate form, that would be a big mess, wouldn't it? That would be a mess. It's going to be the same graph as if I graph this. Now, which one would you rather graph? I would rather graph 2 plus 2 cosine. We're going to graph next time. I promise you it's just easy. Trying to graph 4x squared plus y squared equals x squared plus y squared minus 2x all squared. Can you imagine plotting points for that? Whew, no. So one benefit of going from one coordinate system to another is easier graphing. All right. How are we doing?